10 a.m. here in Kingdom. So good morning, everyone. It's my great pleasure to welcome you all in the 10th seminar of our Saudi Aramco Cybersecurity seminar series. The title of today's seminar is The Art and Science of Fuzzing. This seminar series is sponsored and arranged by Saudi Aramco Cybersecurity Chair at Imam Abdulrahman bin Faisal University. And today we will see how software testing can be performed, how we can extend the test, and there will be many opportunities for the research collaboration with the professor. And I hope this will be beneficial for all our participants. My name is Nasr Minallah. I'm a professor of computer science, and today I'll be moderating this session. So we will divide this session into two sub-sessions. In the first session, speaker will present his talk in 40-45 minutes, followed by 10 to 15 minutes Q&A session. You can type your questions in the chat window, and I will try to read it out in the Q&A session to the speaker. Now let me introduce Professor Thorsten Holz, who is a faculty member at the CISPA Helmholtz Center for Information Security, Germany. His research interests include technical aspects of secure systems with a specific focus on system security. Thorsten received a diploma in informatics degree in computer science from RWTH Aachen University in 2005 and the PhD degree from University of Mannheim in 2009. Before joining CISPA in October 2021, he was a full professor at the Faculty of Electrical Engineering and Information Technology at Ruhr University, Bochum, Germany. With this, now I will ask you all to please join me in welcoming Professor Thorsten Holz. With any further ado, Professor, now over to you, please. You may start.
Okay, yeah, thanks a lot for this introduction. I'm sharing my slides, and you should now see the first slide, right? That would be great. Okay, thank you. Yeah, thanks a lot for this kind introduction. My name is Thorsten Holz, and I'm very happy to talk today about the research we've been doing. So unfortunately, I cannot turn on the camera. So in case you still give me this permission, or we can also do this later on during the Q&A session. It's also fine. Okay, today I want to talk about recent research we've been doing in the area of software security. So about 5 years ago, we worked a lot on return-oriented programming and control flow integrity. But since then, especially in the recent 3 years, we worked a lot on testing software efficiently for potential vulnerabilities. And in about 40-45 minutes, I want to give an overview of some of our key results, and I'm happy to answer questions. So in case something is unclear, please let me know. The work I present today would not have been possible without my great team. So here you see an overview of me and my research students. I'm actually the person right in the middle of the picture. And as you see, we have a rather large group of PhD students. And this helps us to work on many different facets of modern computer security. So the main themes we follow in my group is software security. So we want to either find vulnerabilities in an efficient and scalable way. And on the other hand, we also work on software defenses. So how can we protect a given system against potential attacks? The main application domain is Windows and Linux PCs, but we also work on server-side software, cloud software, or sometimes also on embedded systems. This has been a main focus, especially in the past year, where we started a larger project on embedded security. And I hope you can still hear me. There's some noise outside. I hope this will stop soon. Other topics that we follow are machine learning and security, because this has been a very exciting area recently, with lots of progress in this domain. For example, with large language models that can now generate code in an automated way. We have deepfakes that enable an adversary to generate realistic pictures that can be used, for example, in social engineering campaigns. Or how can we use machine learning in order to efficiently detect ongoing attacks, such that we can react towards an ongoing attack in a very early phase. And the third research theme that we follow is mobile security. So several of my students also work on LTE and 5G. And we, for example, uncovered several specification flaws in the LTE specification that enabled us to eavesdrop on communication, or we were able to divert a network connection from the victim's phone to a server that we control without the victim noticing that something is going wrong. So as you see, software security, machine learning security, and mobile security as three areas. But today, the main focus will be on software security, because this has been the area where we were most active in recently. So we published more than a dozen papers on this whole topic, mainly related to fuzzing, so how to efficiently find software vulnerabilities. Okay, it seems like I can open the video, so let me try this. So now you should also be able to see me. Okay, thank you. So on the slide, you see an overview of some of the recent keywords that we used in the abstracts of our papers. So you see fuzzing, fuzzers, code, programs, antifuzz, grimoire, and several tool names. And I will provide an overview of what this whole research theme is all about. The starting point for us is the system, and the system that we want to analyze. So basically, you can think of this either being some kind of program. So this can be something like a user space process, so a web browser, or a Microsoft Office, or some other kind of program with which a user interacts. It can also be a library, something like a cryptographic library like OpenSSL, which we want to test for potential vulnerabilities. But the system, so we have a rather broad definition here, can also be something like an operating system kernel, something like the Linux kernel or the Windows kernel, or it can be a hypervisor, so something like VirtualBox or other hypervisors that power the modern cloud infrastructure. So basically, programs deeper in the computing stack, where we have the operating system or the hypervisor, and we also want to test these pieces of code for potential vulnerabilities. But the system that we're interested in can also be an embedded system, so it does not need to consist of software only. It can be something like a PLC, so programmable logic controller, so basically one of those devices that power embedded systems. It can even be something like the CPU itself that we want to test for potential vulnerabilities, or embedded devices such as a smart bulb, something like this. So this is, or these are examples of the systems we are interested in testing. What we also have is some input that we can send to the system. So for example, for a web browser, we can send to the browser a piece of JavaScript code or an HTML page that the browser then renders. For OpenSSL, we could interfere with the library, for example, by issuing a sequence of calls to the library. For Linux, it could be a sequence of systems calls that we issue, similar like for hypervisor, a series of hypercalls, or with the CPU, we could try to execute command sequences that might lead to undocumented instructions, or we can try to find side channels in an automated way. And finally, for an embedded system, we could interact with the embedded systems by sending inputs via different kinds of peripherals, typically via IO-MMU, such that we can interact like a malicious peripheral and send inputs to the system. So the system that we want to test on the one hand, and on the other hand, a particular input that we can send to the system. And the basic idea of fuzzing is really simple. So what we do is we send the input to the system that we want to test, and then we observe what the system is doing. Ideally, it crashes or shows some kind of anomalous behavior. And then what we do is we mutate the input. So these are these zeros and ones. So for example, we flip a few bits in the input from 0 to 1 or from 1 to 0. We append a few random bits to the end of a message, or we cut out a few bytes in the middle of the input sequence. So we have several mutation operations that enable us to mutate the input. Then we send this mutated input to the system that we want to test, and again observe how the system reacts to our mutated input. So really simple dynamic analysis where we send randomized inputs to the system under test. And the key idea here is that we do this on scale. So we do this with not only a few hundred inputs that we send to the system that we want to test, but rather hundreds of millions or maybe billions of inputs to the systems. And the main concept is rather easy and well known for some time. So in 1988, this was actually a class project by Barton Miller, who used this as part of his class on security, because he observed that when he sent random inputs to command line utilities, those utilities crashed. He turned this into a class exercise and also coined the term fuzzing. And by now, this has been a very active research area, especially in the past years, where lots of progress has been reported in this area. And fuzzing is these days the main effective or the most effective way to find vulnerabilities on scale. Initially, I was a bit hesitant whether we should also do research in this area, because in the past, we worked a lot on static and dynamic analysis. So we built all these textbook style analysis tools based on control flow graphs, data flow analysis. Then we generated formulas, let them solve via an SMT solver. And this actually worked in practice. So we had actually quite a lot of project in this space. I also had a so-called ERC grant on analyzing embedded systems via this kind of, let's say, computer science heavy analysis methods, and we found vulnerabilities. But then one of my PhD students actually convinced me that we should also start to take a closer look at fuzzing. This was around the time when AFL and several other tools were developed, because they were a game changer. By just using this kind of randomized inputs and doing the mutations in a clever way, and then also detecting that something went wrong, we were able to way more efficiently find vulnerabilities with much less development effort. So since then, I have hired probably about a dozen students who work on fuzzing. So this is the main theme in my group since the past few years. Still in my heart, I do not fully understand why fuzzing works so efficiently, but I think one of the key insights is that this can be done very efficiently. So if we engineer a system that can perform about 500 executions per second, so 500 tests that we can send to the system under test per second, then this turns out to be more than 40 million executions per day. So just on one machine, we can test more than 40 million inputs. We can scale this to more machines. So by now we have about 40 machines which we can use for fuzzing. And if you do the math, you quickly see that we can do hundreds of millions of tests easily. And then eventually we will also find interesting inputs that lead to interesting behavior. So you can think of this as this horde of monkeys that randomly type on typewriters, and eventually they will come up with Shakespeare. And this is to a certain extent also what we do with fuzzing. So of course we have clever ways how to do the mutations. We sometimes use domain knowledge about the system that we want to test, and then just via brute force, and modern CPUs are amazingly fast, we can do this very efficiently. The main theme that we follow is so-called coverage-guided fuzzing. And I will explain how this works in a basic way in the next few slides. Again, in the middle, we have the system under test. So a browser, an operating system kernel, or some kind of embedded system. For this system, we also have a representation of the code that it is executing. So on the right-hand side, you see an approximation of the control flow graph. So how the individual instructions of the program interact with each other. So here we, for example, see that there are several, this could be if statements, where we can branch between different regions of the code. And then again, we have the input that we can send to the system under test. We also have a way to observe how the program is reacting. So we can basically somehow instrument the system such that we can observe what instructions are currently being executed. How this is realized depends on the actual implementation, and I will explain how our approach works in the next few slides. But for now, just think of this as a way to observe how the system is reacting to the input that we send to the system. And what we then do is we follow the approach that I outlined earlier. So we have the input, we mutate it, send this mutated input to the system, and then observe how the system reacts. So now color-coded in green are these areas of the program that we can execute with the when we send this input to the system under test. The main goal of our approach is to maximize coverage. So we want to generate inputs that reach deeper parts of the program state, because it's the necessary precondition to reach a potentially vulnerable location. And only if we're able to reach deep into the program, then we have a chance to also uncover vulnerabilities. So we want to maximize coverage. Therefore, this whole theme is called coverage-guided fuzzing. In the second step, we again follow the same approach. We mutate the input, send this mutated input to the system under test. But now the second mutated input executes the very same sequence of instructions that we had already observed when sending the first input to the system under test. So therefore, the second input is actually not interesting for us, because we already know with the first input how to reach that part of the code. So basically, we can throw away the second mutation because it does not provide any meaningful feedback to us. In the third step, we again perform a mutation, send this mutated input to the system under test. And here, this mutation provided us with some progress. We can now cover more regions of the code because, for example, we have flipped a specific byte sequence such that a comparison now does not lead to true, but to false. So we can explore another part of the program state space. And so therefore, the second input is then interesting for us, because the combination of the first and the second input now already enables us to execute all these instructions that are color-coded in yellow now. Internally, what the fuzzers are doing is they encode this matching in a so-called bitmap to have an efficient way how to represent the already covered branches in a program, and I'll come back to this later on. And what now drives our research is the question or the challenge, how to reach deeper parts of the code. So how can we make sure that we maximize coverage? And then we also need ways to efficiently detect whether something actually broke. So therefore, in the first step, what we did is we analyzed the state of the art by then and identified several challenges as some roadblocks. So typically code constructs that fuzzers are not able to efficiently provide inputs for. And we found especially two cases that are challenges. The first one is, imagine a program that checks whether the input starts with a specific magic number. So for example, many types of file formats have a header, and only if the header matches, then the program actually processes this input. And you can imagine that if you would randomly need to guess such a magic number, the chance that just via random mutations you hit exactly this magic header, magic value is pretty low, because the chance that you generate an 8-bit value in a just randomized way is pretty small. So therefore, reaching this bug number 1 is actually challenging, because our random mutations where we just flip bits or append bits to the end or cut messages in the middle will not be able to correctly generate this magic number sequence. Another typical example that we found is something like nested checksums, such that the program processes the input and then computes a checksum in order to make sure that the data was not tampered with or was not corrupted in the past. So checksums are a common programming paradigm, and here on the example you see a rather complex type of checksum where we have 3 nested if statements, where the first 2 make sure that specific subsequences are correct, and then the third if statement makes sure that the input ends with R and Q. If you take a look at the slide and analyze the code, you might after some time come up with an example that bypasses all these 3 if statements to reach bug number 2. But you can imagine, just here is how a valid checksum looks like, that this is pretty tough to generate via randomized mutations, because the fuzzer would need to generate exactly this byte sequence, and everything needs to align such that bug number 2 is reached. So again, this is an example of code that is pretty hard to test in an automated way. But if you take a look at both examples, you see that the program itself knows what to expect. So in the first example, the program checks whether a specific byte sequence is available. In the second example, the program checks step by step whether the input matches the expected format and whether a valid checksum is provided. So therefore, what we can do is, by closely observing how the program processes the given input, we can interfere what kind of checks are performed. We can observe what kind of comparisons are being performed on the input, and then use this as a feedback for the fuzzer. So we can actually use the program itself to guide our fuzzing process if we observe what kind of comparisons are being performed. And this is the basic idea of a paper that we published at NDSS with a concept that we call input to state correspondence. So the basic idea is, if we have a specific input, and here on the left-hand side, we have a specific value that we send to the program, this value is somehow reflected in the state of the program, because the input is processed by the program. So somehow the state of the program is influenced when this value is being processed. In the easiest way, we can actually observe the program and directly observe the value that we had sent to the program earlier. So in this case, this would be a direct one-to-one correspondence. So you can think of this as a program that reads in the input and then performs a comparison of the provided input against other internal state variables. So here, this would be the easiest case. And by instrumenting the program and observing all comparison operations that are being performed, we can try to find out how this value that we sent is then later on processed and how it influences the state space. In practice, it's typically way more complicated. So typically, a program performs some kind of transformations on the input. For example, the input is turned to ASCII or to integers, to lowercase or uppercase values, or some kind of computations are being performed on this input that is processed by the program. But here again, what we can simply do is we can test all different kinds of encodings. And in practice, we found that there are about a dozen types of encodings that are typically used by a program, and we just randomly test all of them. Because remember, fuzzing, we can do this efficiently. It's basically a brute force way how to tackle the problem. And then this enables us to overcome the 2 roadblocks I mentioned earlier. For example, for the magic header value, we would see that a comparison against a specific byte sequence is being performed. we see against which input this is being compared to, and we can provide this input back as a feedback to the fuzzer, such that in the next mutation, the value is changed such that it corresponds to the magic header that is being expected by the program. To make sure that this works in an efficient way, we've actually worked on a lot of engineering tasks in the past years. And here on the slide, you can see an overview of the basic setup that we use for many of the papers that we have published recently. The starting point is a paper published at Usenet Security 2017 called KFL. And KFL is basically a custom hypervisor. So basically what we do is we assume that we have an Intel CPU, because we also use some processor features that I explain later on. So we boot the hypervisor, and then in the hypervisor, we can boot virtual machines. And here you see 3 examples of the virtual machines. And the hypervisor is optimized for fuzzing. So basically, it provides us with some primitives that we can use to mutate inputs to observe that something interesting happened. And especially, we have an efficient tracing mechanism. And this is, again, where the Intel CPU comes into play, because we exploit a feature called processor trace, so Intel PT, which means that the processor itself tells the hypervisor whenever a branch is occurring. So whenever we jump from one code location to another code location, the processor informs us that a jump has occurred. So basically, the CPU itself helps us with the tracing, because we receive information whenever the code jumps from one location to another one. And this is exactly what we're interested in. Remember earlier this code layout I had on the right-hand side, where we need to observe what code region is currently being executed. Then red green is the concept that I explained earlier, where we can observe what the system that we want to test is currently doing. So we instrument all comparisons and then make sure that we use this as an additional feedback loop to provide more meaningful types of computations or mutations. Sorry. Then in the virtual machine, we can then either test the kernel or the user space, and I provide a few examples of projects in the next few slides. In the first step, once we have this setup of having a hypervisor-based fuzzing framework, we can also start within our hypervisor another hypervisor, such that we have this nested hypervisor set up. And then in this nested hypervisor, we can again start a kernel and user space. So, for example, a Linux kernel and then some programs. And then we can test the nested hypervisor, because what we control is KFL. So we control the underlying hypervisor. We can control the kernel. And then we can basically send hypercalls, so instruction sequences or interactions from the kernel back to the underlying hypervisor. And then we can test how this nested hypervisor reacts to our input. And this is exactly what we do within Hypercube. So the basic idea is we have our custom operating system that runs a kernel that's, again, optimized for fuzzing. We have KFL and the other underlying infrastructure, and then we use this in order to test a hypervisor for potential vulnerabilities. The paper was also published at NDSS, and this actually works well in practice. And here you see a rather broad overview. I don't want to get into too much detail, but because I already explained the main building blocks on the previous slide. But what we have in the middle is basically an interpreter that generates random sequences of interactions from the operating system to the hypervisor that we want to test. For example, we can issue hypercalls, we can access model-specific registers, we can interact with PCI or ISA devices, or perform, for example, APEC operations. So basically, we randomly poke around and interact with the hypervisor that we want to test. And again, This mainly works because we can do this very efficiently. So here on the left-hand side, you see an overview of the hypervisors that we tested. VMware Fusion, VirtualBox, QEMU or KVM, and Acorn is, for example, a hypervisor developed by Intel and a consortium. And in each of them, we found some vulnerabilities. More than 40 of them were security relevant. So this is basically an example of how we can use the framework and the tooling that we have developed to efficiently test complex pieces of code. Then it turned out that, or one of the other problems we stumbled across is that fuzzers have a problem to efficiently explore programs that use complex state machines. For example, if you have a cryptographic library that you want to test, you first need to interact with the library, set up a context, then send a sequence of calls to the library to bring the program into an interesting space, and only then you can do actually meaningful kinds of interactions. Or let's say you want to test the baseband of a mobile phone for potential vulnerabilities. Therefore, you first need to authenticate, you need to establish a connection, and only then you can do meaningful types of interactions. And this is something where the fuzzers actually have a problem because they do not have the concept of a real state space, and for them it's really tough to explore such state machines in an efficient way. And the main problem is that fuzzers use a bitmap, so basically a coarse-grained and lossy representation of storing what kind of state they have already explored. This is mainly an optimization problem because a bitmap is used to have an easy and a very efficient way to store information, but two entries next to each other in the bitmap do not have any semantic meaning. So this does not mean that two branches that are next to each other have been explored, but these can be random locations within the binary because the bitmap abstracts away from the concrete branches that have been executed. And so the basic idea, what we followed here, is that we come up with a set of annotations that enable a human to guide the fuzzing process, such that we can basically provide additional feedback, additional entries in the bitmap that help then the fuzzer to decide what kind of input was interesting, and then we can guide the fuzzing process. So the basic idea is to provide a human with another interface to interact with the fuzzer, such that the human can guide the process, and the fuzzer has this whole brute force tools in order to efficiently explore the state space. What we did in the first step is we tested libtpms, which is a library implementation of a trusted platform module with AFL, and AFL is one of the most prominent fuzzers. And what you can see is that the fuzzer was able to find several states. So each dot is basically a state, and two nodes are connected with an edge when there was some kind of transition. So to a certain extent, AFL is already able to explore the state space of libtpms, but in practice, libtpms is way more complex because, as I mentioned earlier, you first need to set up a context, then interact with it, send some kind of commands to it. So an example of a very complex state space. We published a paper at IEEE Security and Privacy, where we proposed the set of annotations that enable a human to interact with the bitmap, so to provide additional feedback, additional guidance to the fuzzer. And with eJON, we can then do this in a much more efficient way. So here we see that, again, libtpms now tested with eJON, and we see that we can find way more states and way more state transitions. Of course, this is rather abstract, and many of the concepts I explained earlier are not that easy to visualize. And therefore, my PhD student Cornelius and Sergey, who were the main drivers behind this line of research, they had a brilliant idea. So Cornelius came up with the idea of using another way how to visualize these concepts that we have developed. And what we came up with is Super Mario. So I think many of you probably know this game. So on the bottom left, we have Mario, and Mario needs to reach the end of the level. Within the level, there are certain enemies that kill Mario. There are several traps where Mario will also die if he falls, for example, into one of those traps. And the challenge here is we need to generate an input sequence to reach the end of the level. So basically what we need to do is we need to generate a sequence of key presses that prevent Mario from being killed, so jumping over all the enemies, over all the traps and everything. And this is similar like what we do when fuzzing a complex program. There we also need to generate an input sequence to reach a specific goal. But here you can actually nicely visualize this, because each run, so each input that our fuzzer generates leads to a specific behavior of Mario. And by visualizing this, so basically by connecting our fuzzer to the game engine, we can then provide some kind of visual feedback of how our fuzzer behaves. And the following video then shows the result of our fuzzer after several minutes of fuzzing. So here you see it has figured out how to jump, that it should, for example, jump over the enemies, jump over these traps. And again, we have not encoded any kind of domain knowledge within the program, but this is just that the fuzzer figured out that in case it dies, so in case it hits the enemy, it will not be able to continue, or it needs to jump over holes, for example. And here what we see is a visualization of this fuzzing progress over time. So you see at the beginning, it figures out that it can jump around by pressing specific key, and jumping around means that it is faster. So this basically means it reaches the end of the level sooner. And this is actually the optimization problem that we give the fuzzer. So we only tell the fuzzer that it should generate an input sequence to reach the maximum X value. And X value to the rightmost entry is the end of the level. And this is already enough feedback for the fuzzer to then figure out what kind of input sequences need to be generated. And here you see that the fuzzer also fails sometimes. So for example, here it falls into these two holes, but over time it will then figure out that it needs to jump in order to not die. And this is then basically the feedback that the fuzzer also finds helpful. Okay, this is an example of how to visualize our progress in eJOHN as a way how a human can guide the fuzzing process. And in the last example that I want to give is NUX and NUXNet. So a paper that we published at Usenix last year and at Eurosys this year, where we pushed this whole hypervisor-based fuzzing one step further. So again, NUX is a further development of KAFL, and NUXNet is then the latest edition. And the basic goal here is, or the main insight is that given that we have a hypervisor-based framework, we can also do full system snapshots. So we can start a virtual machine, and in the virtual machine, we can then start a program and then also do a snapshot. Then we can process a bit of input and then do another snapshot. We can then again process some kind of input. And if we find that this input did not provide any kind of meaningful progress, we can also restore a snapshot. So the power of the hypervisor is that we have full control of the virtual machine. We can do arbitrary snapshots, restore these snapshots, and then use the snapshot features to efficiently explore the state space. We then also build this, and the tooling is a bit complicated. So therefore, I just want to explain the main concepts. So in the middle, you see NUXNet, which is our fuzzing framework. Then on the left-hand side, this is mainly configuration information. So basically just a specification, what kind of software should run within the virtual machine, what kind of seed inputs, so what kind of inputs should be provided to the system under test. And then also a specification, which is basically a guidance for the fuzzer how to perform mutations. On the right-hand side, you see the virtual machines. So first, we start a virtual machine, set it up in a way that basically represents the system that we want to test. And then we can do a snapshot. We can execute some input, restore the snapshot, again, process some input, and do this over and over again. So basically, snapshots and full system restores as a way how to do this efficiently. Of course, you might now wonder, is this really efficient? Because doing a full snapshot of a system sounds like a costly operation, especially if we need to restore this often, then this is something that might require quite a lot of computational resources. But it turns out that you can also optimize this a lot. So here you see an overview of the performance for either creating snapshots or restoring snapshots, so how to load them again. And in red, you see NUXNet, which is our implementation. Agamotto was a kernel fuzzer published at Usenix Security 2020. And we use this as a bias baseline to compare to. And what you can see is on the x-axis, the number of dirty pages. So a page is dirty, so a memory page is dirty in case it is modified, because we then need to take care of either doing a snapshot or restoring the snapshot for all the memory pages that have been modified. And on the y-axis, you see the number of executions per second. So what you can see is if we do not perform many interactions and therefore do not dirty many pages, then we can do more than 1,000 snapshots per second. So this is rather efficient. For loading snapshots, this also works, where we can also do hundreds or sometimes more than thousands of snapshots restores per second. But this also heavily depends on the number of pages we modify. So if we modify more than 1,000 pages, then the performance drops because the snapshot restore needs to take care of restoring quite a few pages. So therefore, this was a lot of engineering effort to make sure that snapshot create and load is efficiently. And this then allows us to do the state space exploration way more efficiently, because here in the Mario example, we do not need to start from the beginning of each level. We do not need to basically move from the beginning to a specific point in the level from which on we want to continue, but we can do a snapshot at that point in time, and then only from there on in the future, so for the future, explore the state space efficiently, and so that we can reuse a lot the input that we have already generated. So red is everything that we have already explored in the past, where we can basically reuse information, and green is only the new inputs that we need to explore. And this basically allows us to step by step explore the state space. We use this, for example, to test web browsers. So again, the setup, Intel PT for processor tracing, Nux as a custom hypervisor, we have a kernel, and then in the virtual machine, we start, in this case, 3 instances of Firefox. And Firefox is a complex program, so it takes a bit of time, so hundreds of milliseconds to basically set up everything. Then we take a snapshot once the browser is fully initialized. And then from there on, we then explore, for example, the IPC interface. This works pretty well. Mozilla is using this setup now internally. They also paid us a bug bounty to reward our engineering effort, and quite a few vulnerabilities were found in the browser via this setup. Okay, and then as last slide, I want to provide a brief summary and an outlook. So with the methods that I presented today, we have tested many different types of software, hardware for potential vulnerabilities. And here on the slide, you see some of the logos. You might recognize some of them, where we basically found vulnerabilities in many types of popular software systems. And yeah, we found hundreds of security relevant vulnerabilities over the past few years. Still, there's a lot of research to be done. For example, it's interesting to explore how we can explore deeper parts of the software hardware stack. Can we, for example, test the UEFI or SMI handler, or even its processors itself? And this is something we are currently exploring. Then, one topic that bothers me for quite some time, but somehow we do not have a good way to tackle this, is imagine we test one program, we can send hundreds of millions of inputs to this program, but when we then start with the next program, we start from scratch. So we cannot somehow reuse the information that we learned in the first hundreds of millions of executions for the next program. So can we maybe come up with some ML techniques? Because this seems to be a bit related to reinforcement learning, but that somehow didn't work out for us. We also tested ensemble fuzzing, so how to combine different fuzzers and come up with a better fuzzer at the end, but this also did not really work. So there we probably need some guidance from people with more knowledge in the ML area. And last, I think we also need better hardware and software support. So can we, for example, engineer a compiler that produces more fuzzing-friendly code, such that basically code constructs that are hard to test in an automated way are avoided, such that the compiler can actually generate code that we can test more efficiently? Or can we extend a CPU, for example, a RISC-V CPU, such that it supports testing more efficiently? And there's been a very interesting project called Vectorized Simulation by Brendan Falk that we use as an inspiration. And I think especially that topic area will guide our research in the next years. With this, I would like to thank you for your attention, and I'm happy to take questions. Thanks a lot. Sure. Yeah.
Thanks, Professor. It was really interesting seminar, and we have received a few questions. Some you have already answered, but I will go through them quickly. So I will also type the questions for the audience convenience. Well, the first question says, can fuzzing be used for performance testing as well? I mean, they're asking that how we can use fuzzy testing for improving our performance of the system.
So two aspects come to mind. First, there has been some work on detecting algorithmic complexity attacks. So basically attacks where an attacker sends an input to the program that leads to a very long computation time. So this can be, for example, used to identify bottlenecks, where, for example, algorithmic complexity attacks, because the input is complex for the program to process, is leading to a degraded performance. On the other hand, but this would require a bit of engineering, would be if the fuzzer provides some kind of feedback that performance or what kind of performance metric you are interested in, then the fuzzer could basically try to maximize performance towards a specific goal or try to minimize performance to a specific goal. So this will likely work. It's mainly related to how to build a feedback loop that the fuzzer can then use to guide the performance metrics.
Yeah, the second question says, how do we will know when to stop fuzzing testing, like when to stop the fuzzy testing? Maybe it takes longer time. So is there any criteria to stop fuzzy testing?
Yeah, that's actually a very interesting question. Excellent question. Thank you. Because this is actually still, to a certain extent, an open research problem. Because what we observe is, let's say we have a given program, we start to test it, but then typically after several hours or several days, we reach a plateau. So basically, we do not have any meaningful progress. We do not reach more code blocks. And this is something, this is still an open research challenge. There's been some work by Marcel Böhmer on analyzing how much input provides still some kind of meaningful progress. But still, this question is not fully solved, I think, because sometimes the fuzzer still has progress. For example, if we then randomly restart a process, this could lead to some interesting progress on the fuzzing end. And companies such as Microsoft or Google or Meta, they let their fuzzing campaigns run for months because eventually they still see some progress. So therefore, I think this is definitely an interesting question to explore further in the future.
Thank you. The next question says, can fuzzing help in avoiding memory leaks? Maybe you can easily detect memory leaks, but can these fuzzy testing based approaches help us avoiding any memory leaks in the system?
Mm-hmm. So what you would need to do is you would need to build some kind of sanitizer that basically observes memory consumption over time. And then by just randomly interacting with the program, you will then, or you might then also trigger memory leaks. But here the challenge would be to detect that a memory leak is happening. And on the other hand, also to guide the fuzzing process to provoke memory leaks. So for example, to execute more allocations, deallocations. So this can probably be built by building a custom feedback and then also building a custom oracle that helps the fuzzer to figure out when a memory leak occurs and then provoking to injecting more memory leaks or more operations that potentially lead to memory leaks. Mm-hmm.
Right. The next question is, some people say fuzzy testing can detect only simple faults or threads. Is it true?
I think it depends on what you call simple. In practice, many fuzzers are related to memory safety issues. So vulnerabilities in memory unsafe languages such as C, C++, because there we have a rather easy way to detect something went wrong because the program just crashes. I'm not sure whether this counts as simple, but what you can do is, and this is definitely also an open area of research, is how to come up with better sanitizers, so better bug oracles. That's something I did not cover in today's talk, but that's an interesting challenge, basically. How can we detect more complex type of faults? And what we, for example, recently built was custom bug oracles to detect something like a privilege escalation, that we can figure out that a sequence of operations leads to a situation where an unprivileged process suddenly has more privileges than it should have. And this would be one example of a more logical type of fault. And on the other hand, for example, if we do browser testing, then we need rather complex types of inputs that we need to send, for example, to a JIT engine that is then leads to JIT code that then triggers a vulnerability. So you can also find very deep bugs which are hard or maybe even impossible to find via manual analysis via fuzzing.
Right, thanks again. The next question says, based on your experience, what is the most effective fuzzy testing tools for web applications?
Again, a great question, because in the web application space, there's actually not much work so far. There have been 2 academic papers on fuzzing web applications, but we found that they are not that promising. So at the moment, we have a paper in submission where we used the tools that I presented today, so Nux, Red Queen, and similar methods to build a fuzzer that can test web applications efficiently. So, and basically you can think of this similar like the Firefox setup I had. So within the virtual machine, we install a web server, a database, and the web application. Then we take a snapshot, and then we use a Red Queen-like method in order to generate inputs to the to the web application. And then we also need custom bug oracles, because in a web application context, we are not interested in memory safety violations, because the web application will not simply crash, but we are more interested in things like the SQL injection or cross-site scripting or command execution. And this actually works in practice. So we can basically use the tooling and the methods that I discussed today to then build a custom fuzzer that is customized for web applications. And the paper is currently in submission. So if, in case you're interested, please send me an email to holz@cispa.de, and I'm happy to share more insights.
Wow, yeah, that was very interesting. Sure, we will let you know. Maybe I will communicate your address with the person who asked the question. Maybe they can approach you. Well, the next question says, how effective fuzzy testing is identifying SQL injections?
Yeah, this is similar like the previous question. So again, we need better sanitizers, because SQL injection does not lead to memory safety violations. So we do not observe a crash, but it's more like a logical type of vulnerability. So an attacker can inject content into a database. So therefore, we need to build a sanitizer that detects that the database was modified. This can be built. So this is part of the project that I mentioned in the previous question. And the challenge is to basically build sanitizers that detect this kind of web application related vulnerabilities.
Right. So the second last question, it says, it's a long one though. I think fuzzing works best for programs that take inputs. So maybe it is useful for websites as well. But can we use fuzzing for websites like bbc.com, where it only shows information and doesn't accept user inputs? Like newspapers, we read news or we get information, but we don't type any input. So they are asking whether fuzzing can help in also detecting bugs in such softwares or not.
So this is also a bit related to the previous question. So how to test a given website, because again, here the attack surface looks a bit different. You would not be interested in crashes or something like this, but rather something like a cross-site scripting vulnerability on BBC, where an attacker can inject JavaScript code, for example, or maybe also something like a SQL injection, although this is probably not possible on bbc.com, but cross-site scripting, for example. And again, you would need to have a setup where you can basically detect that an error occurred. So this kind of bug oracles or sanitizers that I mentioned earlier. But the challenge again here would be that you do not really control the other end. So ideally, you would have a copy of bbc.com that you can run locally for testing. Of course, you could test on the live side, but I would advise not to do this, so not to attack BBC. So typically, the testing should be performed in a controlled lab environment where you can fully control everything. So I think the software that is powering bbc.com could be tested if this is available under some open source license. But else, it's probably challenging to do this test on the live side. And again, you would need custom sanitizers that tell you that an error occurred.
Thanks. We received a new question. It says, how fuzzy testing help in detecting DDoS attacks?
So DDoS attacks, I'm not sure against what the context of the question is, but what is possible would be something like reflective DDoS, so where an attacker sends a short input sequence to a server, and that input is then replied to in a longer message to the victim that should be attacked, so to really via UDP spoofing. There has been a work published at Usenik Security this year that performed this kind of fuzzing to identify services that can be abused for DDoS attacks. But detecting DDoS attacks against a victim network is not possible with fuzzing, but rather identifying potential infrastructure that can be misused. And again, I refer to the Usenik Security paper that was published by a colleague of me. So Christian also is his name.
Right. So one more question just came. How machine learning improved the fuzzy process and results?
Definitely interesting open question. I mentioned that we spent a bit of time on doing this, but unfortunately we were not really successful. So we, for example, tried this ensemble fuzzing. So we combined different fuzzers, similar like ensemble learning, and in ML, ensemble learning is a great way to do this. In fuzzing, we figured out, or we didn't really figure out a lot of progress, so this was not really a successful project in that sense. Or what I mentioned earlier with reinforcement learning, because you can, so intuitively I would formulate fuzzing also as a reinforcement learning, where we have two computers that compete against each other, but somehow this did not really work out well for us. We tried to formulate this as a bandit problem, but that also didn't work. So for us, we had different methods that we tried, but were not really successful. So in case you have ideas, please reach out, happy to discuss. This has been an exciting area, but we were somehow not able to really exploit ML for having meaningful progress in fuzzing.
The last question, and just 1 second. Okay, so last question says, how effective is fuzzing in comparisons to static analysis and pen testing?
Okay, that's also a great question. And I think there's probably no general answer to this. So therefore, a few observations. So static analysis is definitely a very interesting approach. It finds lots of different types of vulnerabilities. Unfortunately, it suffers from false positives. And actually, we have an ongoing project at the moment where we have a set of fuzzing tools, a set of static analysis tools, and for a specific or different kinds of benchmarks, we analyze how effective fuzzing is compared to static analysis. For example, what kind of bugs can be found via static analysis that a fuzzer cannot find, or how many false positives does the static analysis tool produce that a fuzzer can not really find, or because fuzzers typically don't have false positives. So this is definitely an interesting question, and I hope to have some answers in the next months to come, because this is actually an ongoing project in my lab at the moment. And pen testing, so basically manual analysis, I think there it depends on how much manual effort you put into this. So you will definitely be able to find other types of vulnerabilities. But in practice, I know, so some friends of me work in this space, and typically what they do in the first step is to set up fuzzing tools, then do manual analysis while the fuzzer is doing the automated analysis, and basically combining pen testing with fuzzing is, I think, a promising method.
The last question is, sorry, I keep asking, this is probably the last question. So it says, how effective is fuzzing for secure, especially in extremely sensitive private information?
Typically, you control everything. So therefore, so the system that you want to test, this is something you should be able to control. So therefore, you can also process or make sure that private information is not leaving the system. So therefore, I think the challenge here is to make sure that the system that you want to test is under your control, and then no privacy leak or anything else should occur, if I understood the question correctly.
Right. So thank you very much, Professor, for the very informative seminar, and we are open for further collaboration. We have a very strong academic program at our college called Cybersecurity and Digital Forensics. So we would like to see opportunities of collaborations. With this, now I will request my dean to thank the speaker and the audience. Thank you.
Assalamu alaikum.
Assalam, Alhamdulillah.
Thanks, Professor Nasr Mallah. Thanks for our distinguished speaker, Dr. Franz Holz. I would like to thank also the audience for their attendance, for their interaction. And also, again, I'd like to thank the speaker for sharing his experience for extensive research in the fuzzing. I believe has added great value to that to the chair lecture series, and looking forward to collaborate in the security testing. I believe most of the attacks come with malicious software, so having good testing will eliminate or at least will reduce such attacks. So thanks again for our distinguished professor and speakers. Thanks everyone, and looking forward to have you on our next lecture series. Thank you.
Thanks a lot for hosting me. It was a pleasure to share insights of our current project with you. Thanks a lot.
Thank you. Appreciate that.
Thank you. With this, we will end the meeting. We will see you after 2 weeks in another seminars of similar level, inshallah. Thank you very much. Assalamu alaikum.
Bye-bye.